Okay, welcome back. So last time we looked at systems of this form. We didn't play much with the B term, but you can do very similar things with it, where you have uncertainty in the model and the maximum extent of this uncertainty is known, as is, of course, your estimate of the model. And we were interested, of course, in a trajectory tracking problem defined by having x of t minus x desired of t tend to 0 as t tends to infinity. So we decided to pre-process, if you want, the question by creating an intermediate variable. And this intermediate variable we called S, no relation with the Laplace variable. And S had two properties. The first one is that S dot contains U. In other words, you have to differentiate S only once to find the control input. And the second one was that if we manage to control S to 0, then we will have solved the original problem, which was to control x of t to xd of t, or equivalently to control x tilde to 0. So we said, of course, each of those requirements by itself could have a trivial solution. Here you just needed the velocity error, for instance, of the, in general, the error on the n-1 derivative of x. And this one, of course, you could just take s equal x tilde, but the subtlety was to satisfy both of these conditions. And so we said one way to do this was to choose S to itself implicitly represent a stable, linear, in this case, differential equation. And so we see if we take this, right, we see that S contains x to the n-1. Okay. So which means that it contains the n-1 derivative of x, and therefore once you differentiate S, you get the nth derivative of x, and therefore you get the control input. So you do get this, this property that S dot contains U. And at the same time, this can be viewed, if you say S equals 0, it's really a differential equation in x tilde, right? And a stable differential equation in x tilde. And so if S tends to 0, then x tilde will tend to 0. Okay, so for instance, in the case n equal 2, you had S equal x tilde dot plus lambda x tilde. In the case n equal 3, you would have S equal x tilde double dot plus 2 lambda x tilde dot plus lambda square x tilde, and so on. So by choosing S this way, based on a stable linear differential equation, then we could guarantee that we satisfy these two properties. Basically, we've replaced our original nth order control problem by a first order control problem. And at the same time, we guarantee that if we solve that control problem, we have solved the original problem. We even said that it was really a reasonably precise mapping. In other words, that if we could only show that S didn't tend to 0, but after a while remained bounded by some constant phi, then this implied that x of t after transients would also be bounded by phi to the lambda n minus 1. So if we have a bound on S, then after transient we get a bound on x tilde, and therefore an original tracking error. And if, for simplicity, if we call this quantity epsilon, you can show that more generally. Not only x tilde, but all its derivatives up to order n minus 1 for I equals 0 to n minus 1, x tilde to the I of t is less than 2 lambda to the I epsilon. It's very easy to show. And it's also described in the book. So it means that once you have this bound on S, you can compute bounds on x tilde and actually all its derivatives up to order n minus 1. In other words, you can compute bounds on the tracking error on the state. So whatever imprecision you have in controlling S itself will translate in an imprecision in controlling the state, of course, but this behavior is just linear, right? In other words, the more it varies, it scales as phi, right? Okay. Questions about that? Okay, so in other words, this S is a true measure of performance error because we can translate any error in S into an error in the original tracking question. So we also said that this, this was kind of an algebraic or a differential equation idea, right? Replace an nth order problem by a first order problem. That this could also be seen geometrically by saying that if somehow we manage to get the system to tend to S equals 0 and stay there, then once we are on this surface S equals 0, which is one constraint, one linear constraint in an n-dimensional space, so it's a hyperplane. So once we are on this surface S equals 0, then not only we stay there, but the equation S equals 0 tells us what x tilde does. Okay? So in other words, this surface S equals 0, which remember always contains the desired trajectory xd of t, the vector. This surface S equals 0 is both a place and a dynamics. Okay? In other words, as soon as you're there and you stay there, you know how you move on it. Okay? And so that's the geometric version of saying we've replaced an nth order problem with a first order problem. The first order problem is to get on this surface, and then the other n minus 1 dimension take care of themselves by the very equation of the surface. Okay? Any questions about that? All right, and then we said, well, we saw it for a second order case, but it would be exactly because of this choice of variables, this would be exactly the same for an nth order case. Okay, we said if we have x to the n equal f plus bu, then we would try to achieve this condition. So we gave a specific way of reaching this surface S equals 0, which was in this form. We called this the sliding condition. And eta is just some small positive constant. So this was called a sliding condition because it meant that we reached the surface in finite time and after that stayed on it, so we slided on it. And we saw that to achieve this, we show this in the case b equal 1, but it would be the same in general. One could use a control law which was composed of two terms. One was a term which basically would make s dot equal 0 if we knew everything. Okay, would keep s dot s constant if we knew everything. And then a term, k sine of s, which for the case b equal 1 was capital F plus eta. So this term k sine of s is basically pushing you back towards the surface. Okay? And because it verifies this property, it's always large enough to overpower any error due to the discrepancy between f hat and f. All right? So it was kind of always the same principle. You have one term which has the right sign, you know, and then it's also not only of the right sign, but in absolute value bigger than anything else. Okay? And so the overall result, therefore, also has the right sign. Okay? So by choosing this condition, we saw that we could indeed achieve this behavior. This, however, as we said, was achieved through this sign term, okay, which was therefore discontinuous across the surface. And we said that made sense because if we had the surface this way and we wanted to tend towards the surface in a robust way, so to allow some uncertainty, okay, it meant that basically the trajectories had to point towards each other to be able to leave that slack, okay. And so the amount of gain here we put was basically how much uncertainty we had plus eta. Okay? So eta, as we said, you know, has to do with how long it takes to reach the surface. But from a practical point of view, you can kind of almost view it as a small positive constant, the same kind of positive constant you would avoid to divide by 0. Okay? So you would use to avoid dividing by 0. In other words, what matters is this term. Okay? This term is what reflects what you know about the dynamics and about the uncertainty about the dynamics. Okay? And then you add this small term here. So that's pretty much where we were. Okay? So we said, well, two things may happen. We stop here and it's perfectly fine. We have this discontinuous term, whose size increases with the uncertainty. Okay? And it's fine. It's fine in the sense that the fact that it will create in practice controlled chattering, as we said, is okay because we happen to be driving, for instance, an electrical motor through pulse width modulation, and so anyway, the control signal is of a chattering nature, so we might as well have it chatter the right way. Okay, so if control chattering is not a problem, control chattering, remember, is due to the fact that we're implementing this term with small delays. Okay, so we basically, instead of going exactly along the surface, we're going to slightly overshoot back and forth. Okay, so if control chattering is okay, then indeed you have a really high performance controller, right? Because it gets you on the surface, and once on the surface, your motion is really insensitive to anything that's happening around. Okay, because your motion is entirely defined by the equation of the surface itself. And in the case where control chattering is not okay, which, you know, it depends on the technology, but it's most cases, right? Then what we'll have to do is say, well, you know, that was very nice. We have a very clean, simple solution, okay? But now we have to deal with this chattering control problem, okay? And so there's a variety of ways to deal with this, and we'll just talk about probably the simplest, the most obvious one, you know, and show what happens then. Questions about that? So that's where we are, okay? So we derived all of this, okay? We saw we had the rather systematic way of doing this, okay, both for U hat and for K. It gives us this control law. If the technology allows, you know, it's for instance an electrical motor with pulse width modulation, then we can just do this, okay? It will mean, by the way, that we need to we need to be able to do this computation also, fast enough, okay, but today that wouldn't be a big deal. Okay. But otherwise we'll have to do something. And again, we haven't played much with b. We assume b equal 1. As you'll see in the book, you have small variations which allow you to do exactly the same thing when you have a gain, okay, an unknown gain, as long as you know the sign of the gain. Okay? And there's various ways to do that. One is discussed in chapter 7, and another way is discussed as an exercise. Okay, so what's a very simple idea? Well, we could say we have a sine function here. In this control law, right? So instead of using this sine function in the control law, perhaps we can do something a little more gentle. Okay, so something which is kind of a sine function. Instead of jumping around at x equals 0 or at s equals 0, we have some smooth transition between +1 and -1. So this thing, just as the sine function, is something you find very often in control and dynamics and optimal control and so on. It's called a saturation function. So strictly speaking, a saturation function is something which goes from -1 to +1, just like the sine function, and that's this transition between -1 and +1. Okay. So that's a saturation function, denoted as sat. Now, intuitively, there's nothing magical about 1, about s equal 1, right? So what we'd like to do is be able to do this transition in some zone which we define, okay? So we'd like to do this transition between, let's say, phi and minus phi for some constant phi, right, rather than between -1 and 1, okay? Which means that instead of using sat of s, we'll use what? Sat of s would give us transition between -1 and 1. Okay, we want to transition between starting at minus phi and finishing at plus phi, right? So simply sat of s over phi. Okay. Yes.
Sorry. So what was the motivation for making the transition happen at, or the saturation happen at plus and minus phi?
Oh, okay. So what are we going to do? We're going to take this switching thing, okay, and try to make it more gentle, okay? Now, more gentle will depend on the system dynamics, the numbers, and so on, okay? So the more gentle has no particular reason to be between s equal -1 and 1. We should leave some freedom to pick some better number than 1, okay, to make it more gentle. It's as if, we were choosing a gain in the control law and say, we'll pick 17. Whatever happens, we haven't even looked at the model, it will be 17, okay? So here we're saying it has no reason to be 1, okay? So we just make it more general by letting this number phi, which we'll define.
So it's not the same as the bounds for...
It will be, but not now. For the moment, we've used the same notation, not to use 15 notation. It will turn out to be very closely related to that for reasons we'll explain shortly. But for the moment, it's just a number. So you can, if you want to introduce an extra notation, feel free to. But it's just a number. Okay. Well, so actually related to that question. Okay, so maybe I'll do a a bigger drawing. Okay, so here we are. And so originally we have u equal u hat minus k sine of phi, right? So we have all these trajectories which tend toward s equals 0, for instance, this way. So that's with u equal u hat minus k sine of phi, minus k sine of s, sorry. Now, suppose now I do not u equal u hat minus k sine of s, but indeed I replace k sine of s by k sat of s over phi. Okay, so instead, we use u equal u hat, the same u hat, okay, but we're going to get k sat of s over phi. So in the control law, we're replacing this switching by something more gentle. So my question is, how does this drawing change when we do that, right? So this drawing, we have s equals 0, which is the surface, which moves along with xd, right? And we have these arrows, which, by the way, strictly speaking, are arrows as seen from the moving frame, right? As seen from the surface. They come towards you, right? But this is just a representation. Okay. How does this drawing change when using, instead of using minus k sine of phi, we use minus k sat of s over phi? Well, you see, sine of phi and sat of s over phi are exactly the same if s is larger than phi in absolute value, right? If s is larger than plus phi, then sine and sat are the same, right? And if s is larger than smaller than minus phi, sine and sat are the same as well. Okay? So it means that in the region where s is larger than phi in absolute value, nothing has changed. Right? The system doesn't know whether you're implementing sine or sat of s over phi because they happen to be the same. So what is this region, absolute value of s less than phi? What does it look like? Well, this is s equals 0, right? It separates the space into, s positive, s negative, right? What's s equal phi? Well, it's somewhere here probably, right? If this is the positive space, right? And with s equal minus phi, it's somewhere there. Okay? So in other words, everything happens the same except in this region, which is limited by s equal plus phi and s equal minus phi. Right? Outside of this region, anyway, sine of s is the same as sat of s over phi, so nothing changes. So, before, we said, starting anywhere, we reach s equals 0 in finite time, after which we stay on s equals 0 and we slide along the surface s equals 0. Okay? What's the narrative now? Well, we were supposed to reach s in finite time, but actually the control is not the same in this region. So we reach this region in finite time. After which, well, there's still no arrows pointing outwards, right? So after which we're stuck in that region. Okay, so before we were stuck on s equals 0, now we're stuck in this region. Okay? What's a reasonable name for this region for people coming from mechanical engineering? Or others, actually. Physicists. Well, it's a small region around the surface, right? It's called the boundary layer in fluids, right? Doesn't have to be small, by the way, but okay. So basically, before we were reaching s equals 0 in finite time and then stayed on it and slided along it, right? Now we're reaching this boundary layer in finite time, and then stay in it. Okay? Which gets back to your question, right? So once we know that we stay in it, right, it means that by definition S is less than phi. Right? So it means that after transients we'll have these bounds with, you know, obtained here with the same notation phi. Okay? So before we were reaching the surface at finite time, and after which we had x tend to xd with a time constant given by the dynamics of S. Okay, so after transient S tended to xd, right? Now we reach the boundary layer in finite time, a little less time actually, and then after transient we can guarantee that S is less than phi, which in turn will imply after transient that we have these bounds on the tracking error. All right, so if we wanted, not sure if it helps, but if we had xd here, right, it means that after transient will be in some kind of box around xd contained in the boundary layer. Okay. And the box will be defined by these numbers. Okay. So conceptually it's very similar, right? Instead of tending to 0, we tend toward a small number. Okay, and instead of having exact tracking after transient, we have small error on the tracking. Presumably small. Again, there's nothing in here that says that phi should be small, right? But just conceptually. You had a question? Someone had a question? Yes.
So by making this condition a little bit more flexible, we have the possibility of having that derivative equal to 0 instead of making sure that it's always less than or some negative number.
Well, you know, basically this doesn't tell you at all what happens here. Okay? Outside, this will still be verified. Okay, so we'll still have this kind of finite rate of convergence towards normally S, but in between there's this boundary layer, so towards the boundary layer. Okay? And in between it doesn't tell you exactly what happens, except, you know, it's given by the differential equation corresponding to U hat minus K side of S of phi. Okay, any other question on that? All right, so in other words, what have we gained? Well, presumably by being able to pick a reasonably large phi, we should make our controller reasonably smooth. We'll get back to that. Okay, but of course, the larger phi we get, in other words, the further away we are from this pure discontinuity, this pure switching, then the more potential error we have on our trajectory, right? The bigger this boundary layer gets, the more potential error we have. All right? So we could stop here and move to another subject, right, in a sense, because, you know, that by now you have most of what you need to know about this. In other words, you know, you have this pure, you can design a pure switching controller, and then by playing with how big phi is, you should be able to make the controller smoother, okay, and therefore avoid this intrinsic chattering that you have to get when you get this, these discontinuities. We're going to try to be a little more explicit, okay, on the choice of phi, okay, but see this more as a back of an envelope calculation, okay. So in other words, now you have your system and you're trying to set phi and you're trying to set it reasonably, okay. And so see this as kind of in the back of an envelope calculation, except the envelope will be reasonably big, okay, because we'll see, we'll have a number of remarks, okay, which are kind of engineering-like remarks, okay. But don't see this as profound math, okay, just, okay. Okay, so take your envelope. So let's try to see a little what's happening, okay. So the question is, you know, can we say something about how well to choose phi? And the first remark, in a sense, is, this k here is f plus eta. F is a function of the state and time. So k is really state dependent and time varying. Okay. So if you want kind of the slope of this thing times k to be constant or to be interesting, you see that it's not necessarily this slope, it's really the slope again times k, right? And so for instance, if you want it to be constant, then phi would need to vary, right? Because what matters is k times, well, k divided by phi, right? If we look at this slope. The problem is if phi starts to vary, we can't just do this very simple drawing because, for instance, if it's shrinking on you, it could shrink faster than you reach the surface, okay? And therefore, if you're inside, you could be kicked out, right? Here, phi is constant, okay? All trajectories go in, so once you're in, okay? But suppose phi is shrinking, if it's shrinking faster than the trajectories that reach the boundary layer, but actually it's not true that this boundary layer is invariant, okay? So if we let phi be time varying or state dependent because motivated by the fact that k of xt is, we have to be a little more careful. In other words, we have to say, to say more explicitly, under which condition will it be true that once we're in the boundary layer, we stay on the boundary layer, okay? So it's very easy to show that before we just use this condition outside of the boundary layer, okay? It's very easy to show. Now we need a slightly more specific condition which involves how phi varies. And that condition will be that 1/2 of d over dt of s squared is less than phi dot minus eta times s. So in other words, you have this extra term. Maybe I'll put it in another color. The time derivative of phi. Okay. So, and intuitively, why is this, right? But it's very easy to see if, for instance, you assume that s is larger than phi, okay? Then what you need is that s minus phi decreases. So it gives you the usual s dot term, but it gives you also a phi dot term, okay? So that's very easy to show. So in other words, the condition you need outside of the boundary layer is this, okay? And intuitively, it makes sense too, not just from the algebra, because what does it say? It says that if phi dot is negative, in other words, if phi is shrinking, you need to be faster, okay? Outside of the boundary layer. On the other hand, if the boundary layer is coming towards you, you could just wait, actually, right? So that's why you get this phi dot term. Okay. But again, it comes from the algebra, just looking at, instead of the distance to s, which is s, right, looking at s minus phi or s plus phi, depending on the sign of s. Okay. So, still on the back of the envelope, right, let's try to see where does this lead to. Okay. So, with u equal u hat minus k sine of s, we had s dot equal f hat minus f minus k sine of s, right? Assuming the control chattering and so on doesn't start interacting with all these presumably fast but unmodeled dynamics such as measurement delays, computation delays, actuator dynamics, and so on. So we had this. So now we're going to use, and k, remember, was capital F plus eta. Now what we're going to use now is what? Is u equal u hat. We'll have this sat of S over phi term. But we're not going to use F plus eta. What are we going to use? We're going to use F plus eta plus something, right? What's the something? Well, you see from an algebra point of view, everything happens as if eta had been replaced by eta minus phi dot. Right? If you redo the algebra to try to satisfy this condition, whenever you had eta, you would have eta minus phi dot. Okay. So we can do that in k as well. And so maybe I'll keep the same color, right? We have eta minus phi dot. Okay, sat of S over phi. Okay, so that's the equation we're looking at for u, right? And so it will give us S dot equal F hat minus F minus F plus eta minus phi dot sat of S over phi. And this again is what we used to call k. Okay. So this is the equation we have. So this gives us this, and this would give us this. Okay. So let's now, we start somewhere outside the boundary layer. We reach this boundary layer, okay, in finite time because we made sure we included this phi dot term in the gain. And after that, once we're in the boundary layer, although now it might be pulsating, okay, now we've guaranteed because of this phi dot term, but once we're in the boundary layer, we stay in the boundary layer, okay? So once in the boundary layer, we stay in it, okay? And therefore, we have what's sat of S over phi in the boundary layer? Just S over phi. Okay? Okay, now, so we have to now assume that as F is reasonably smooth and the corresponding capital F is reasonably smooth. Strictly speaking, one would have to assume that they are Lipschitz. There are Lipschitz conditions on these functions. So you could get more technical about this. Okay. What we would like to be able to say is, so once in the boundary layer, this is true, but it's certainly correct, okay? And also once in the boundary layer, after some transients, these equations are going to be true. All right? So in other words, the real state and the desired state will be within something of the order of epsilon of each other. All right? And under some reasonable smoothness condition on F, okay, it will mean that the value, let's say, of F hat at X will be the value of F hat at X desired plus something of the order of epsilon. Okay? So after transients, X tilde is something which is of the order of epsilon. And so all of these quantities are what they would be along the desired trajectory, plus something of the order of epsilon, okay, strictly speaking, a Lipschitz constant times something of the order of epsilon. So what does it mean? It means that you can write S dot is equal to f hat d, meaning the value of f hat, which is a function of x and t, computed for x equal xd, minus fd. Okay, so in other words, these are all values computed along the desired state. There's going to be this k sub d, similarly, minus phi dot. S over phi is less than 1. Okay, so that if we multiply it by something of the order of epsilon, we get something of the order of epsilon. And so we just leave that term at the end. Okay, so this is an approximation, right? Is just saying all of these terms, because once we're in the boundary layer, we stay in the boundary layer, and therefore, after transients of time constants of the order n minus 1 over lambda, we have these bounds, then we can write this. And remember, I've used the fact that S over phi is less than 1. So we can reorganize this a little. It's the same equation, I'm just going to write it slightly differently. It's exactly the same equation, right? I've just reordered the terms. Okay. Now, what does this equation say? It says as a first order dynamics, which gives me S. That's not surprising, right? Because we defined S precisely so that its dynamics be of first order, okay? And that's this dynamics, okay? So in other words, something which is driven by f hat d minus fd plus something of the order of epsilon, okay? That's not how, this is not what you implement in your controller, right? What you implement in your controller is this, okay? This is just trying to analyze what's happening in the closed loop system. Okay, so we have S dot is equal to this plus this kind of input term. And so we've put the same input term here. Okay? And this block here corresponds to this terms times S. Now, by definition of S, the relation between S and the tracking error is simply an n minus 1th order filter, linear filter, which gives us x tilde. Okay? Again, this is just meant to analyze what's going on. It's not meant to be implemented in your computer. What's implemented in the computer is the control law. Okay, so here we have this n minus 1th order filter. And here we have this first order dynamics. Okay. Now, getting back to a question that one of you asked last time and that we mentioned, right? What are we trying to do? We're trying to select phi basically so that what's going on in the control law doesn't get anywhere near the kind of time constants that model, that describe the fast but unmodeled dynamics that we've neglected, right? So in other words, here where I say U equal, it means I have instantaneous measurements, instantaneous computation, instantaneous actuator, right? None of these assumptions is true, of course. That's what's called high frequency on model dynamics, okay, or fast on model dynamics, okay? And so what we're trying to do is that basically be consistent, that nothing here gets any faster or gets near, within a factor 3 or so, of these fast on model dynamics, okay? Because then we don't really know what's going on, okay? So it's just the idea. That's why I'm saying it's on the back of the envelope, right? It's just, okay? Now, what can we say about this first order term? Okay, so first of all, of course, it's easy to choose lambda. We still haven't said how to choose lambda, right? But it's easy to choose lambda to be a few factor 3 or factor 5 of these unmodeled fast dynamics, okay? So that's easy. The question is more this term, okay? Because this is first order nonlinear dynamics. Okay? However, we haven't yet chosen phi. Our question is how to choose phi well, right? So, you know, being very optimistic, you can say, well, suppose this term was exactly lambda somehow. Then I would get 1 over d over dt plus lambda here. And, you know, that would be quite simple, right? I would have all these time constants of order 1 over lambda here, and an extra one of order also 1 over lambda here. Okay? Now, is that possible? Yes, it's called algebra, right? How do we do this? Well, we just let phi dot plus lambda phi equal kd. That will give you exactly this. We just solve this block equal lambda. Okay? Initialize phi any way you want, non-zero, okay? For instance, such that the original phi dot is 0, for instance, if you want. Okay, so if we let phi plus lambda phi equal kd, that exactly solves this equation, this equal lambda. Okay? And therefore, it gives us exactly this block here. Okay? Now, can we do that? Yes, because we haven't selected phi yet, right? So this is how we'll select phi. And we'll see, of course, it will be time varying as we gave it the freedom to be. So in other words, we can get this block here to be simply this first order dynamics by definition of phi. Okay? So we started with uncertainty on f. That gave us k. This term k in terms gave us u equal u hat minus k minus phi dot set of s over phi. We still had to define lambda and phi. For the moment, they were just numbers, okay, positive numbers. Lambda we chose, we'll come back to that, to be nowhere near the time constant involved in the neglected fast dynamics in the model. Phi we picked to verify this equation, which gives us a construction for phi, right? We implement this equation on the computer, right? The discretized version is just one line, okay? And this gives us this. All right? And so at least on the back of this envelope, we have a reasonably complete story, right? Okay, of how to pick lambda, how to pick phi. Okay, reasonably simple choices, which will give us this structure. Okay. Now, and again, I insist this is just trying to analyze what's happening to the closed loop. This is not what you implement on the computer. What you implement on the computer is the equation of u. Okay. This is just trying to analyze what's happening in the closed loop. Now, in the process, actually, of this approximate analysis, you get a useful little tool, especially when you deal with multidimensional systems. So when you'll have, you know, not just S, but S1, S2, Sn, okay? You have several degrees of freedom, okay? So when you have a failure in a system like this with lots of dimensions, okay, whether it's aircraft or a nuclear plant, right? There is a problem, kind of almost a human factors problem, which is called the Christmas tree effect. Okay? And the Christmas tree effect is that you have all these lights, okay, or perhaps on the computer similarly, okay, which turn on when something is wrong, okay? Except when something is very wrong, they all turn on at the same time. And so you don't know what's happening, okay? So the Christmas tree effect is the problem that you have all these sensors that detect errors, except when there's a big error, most of them turn on. So most of them realize there's something wrong, and then you don't really know where to look. Okay. So it's nice to try to have kind of more concise way or more informative way, if you want, to describe what may go wrong, if you want. Okay. So there are these things called S trajectories, okay, which, you know, you can plot in real time on a moving window, okay? And so what are those? Well, so first of all, you plot S as a function of time, okay? So it does whatever it does. So this is S. Now, S, of course, is this intermediate variable that you've created, okay? But, of course, x tilde is a filtered version of S, okay? And you know that if S is less than something, then x tilde will be less than something divided by lambda to the n minus 1, okay? So when you look at this, if you assume lambda is, you know, big enough so that, you know, it's, you know, still the bandwidth, with a quote, the bandwidth, the reactions of the system are reasonably fast, then you know that the error is going to look pretty much like this, more filtered and divided by 1 over lambda to the n minus 1. Okay? So in other words, by looking at S, you're also looking, in a sense, at x tilde. Okay, except not exactly at x tilde, but in terms of, you know, range and amplitude and so on, you know reasonably well how to relate S and x tilde, right? Remember also, this is just a sequence of first order filters, so it has no overshoot, right? So you have this bound between S and x tilde. So if you look at this, you look at S, but it gives you also a pretty good idea what the tracking error is at time t, you know, if you assume lambda is fast. However, S, you know, is also this weighted combination of position error, velocity error, and so on, right? So if there is noise in your measurements, especially in high order measurements, you'll see it in S, and you wouldn't see it in x tilde. Right? So whatever noise you have on x dot, x double dot, and so on, you'll see it in S. It will look much more noisy. You wouldn't see it on the most filtered version, which would be the tracking error. Okay, so if this gets really noisy, you figure out, you know, there's something wrong, or at least not done well enough with your sensors or with your observers or something like that. If this plot gets really noisy, okay, which you wouldn't see in x tilde. Okay, so that's the first remark, if you want. Now the second remark is that you have this phi, right? So this phi you could plot as a function of time. And it looks like this. And let me plot the other one. It's supposed to be minus phi. Except, of course, maybe I shouldn't have picked such a complicated one, but anyway. So this is phi and minus phi. Okay, and this contains several amounts of information as well, okay? First of all, it means that, you know, suppose the orange curve is basically along the x-axis in this plot because phi is so much bigger than S, okay? Basically, you don't see the orange curve, right? It means that your assumption on the uncertainty are way too conservative, right? Because basically you picked phi, which was some filtered version of KD. KD was itself the uncertainty capital F, right? Fd, right? So if S is much, much smaller than phi all the time, it means that basically your assumption on the uncertainty are way too conservative, okay? Conversely, of course, if S gets way out there and comes back, it means that your assumptions are not conservative enough, okay? But perhaps if F gets way up there, comes back, and nothing else happened, it means that your modeling is not very good in this region of the state space where you happen to be now, right? You know, if you happen to get out here and then back, it means you have more uncertainty happening now, perhaps because the velocity is in this region or whatever, you know, and then maybe you should do a better job at modeling there. Okay? And of course, implicitly, this also says, you know, phi is a filtered version of KD, right? So it's simply a fast filtered version of the uncertainty as a function of time, as a function of where you happen to be in the desired state. Right? So it also tells you that, okay? And suppose you have a rather common motion and phi itself is all over the place, it means you're not doing a very good job at modeling, you know, because half of the time phi is huge and half of the time it's really small on a normal operation, which means your modeling was very uneven. Okay? So you can see that on this one plot of S phi and minus phi, you can see a lot of things, the actual performance of the system, the effective noise, okay, or you can detect, let's say, a lot of things, the actual performance of the system, the effective noise, the validity of your assumption, whether conservative or not, on the modeling error, okay, and the quality of the terms you picked in the model to best minimize this modeling error. Okay, and it's all in this one plot per degree of freedom. Okay. Okay. So that's a useful tool when you play with these systems. Okay. Questions about that? Okay, so still with the same flavor of, you know, approximate calculation to see what's going on, right? So we know that we have these after transients, these bounds after transients. We also know that phi changes, okay? So suppose we, just to understand roughly what's happening, we decide to neglect all time constants of the order of 1 over lambda. In other words, we assume that these are reasonably fast dynamics. Of course, nowhere near as fast as the unmodeled dynamics, but still, you know, system is reacting well. So if we neglect time constants of the order of 1 over lambda, okay, then very, very roughly speaking, it means that phi is like KD over lambda, right? There's not much of a filtering and you just get the DC term. And we also know that we have this bound, okay? Lambda to the n minus 1 times the maximum value of x tilde is roughly equal to phi. Again, you know, there are dynamics floating around, but we assume they're fast. So you have phi, which is of the order of KD over lambda, and lambda to the n minus 1 times this, which is the order of phi. So if we pick the two together, it says that lambda to the n times the maximum value of the error is of the order of KD, which is itself FD, remember, because we said eta was a small term. Okay. So that's not very surprising, because in a sense, that's what this drawing is also telling us, right? It's telling us basically you have this, if you analyze what's going on, you know, you have the uncertainty on F happening here, which drive this first order linear system, which drive this nth minus 1 order linear system, which gives you x tilde through the intermediate of S. So basically you have something which would be very much what you would have if you had a linear time invariant system with disturbance, a constant disturbance. Right? What is the error you would get? You would get the disturbance divided by the DC gain. Right? So that's basically what you get here. You get the disturbance divided by the DC gain for the error. Okay? Except, of course, it's in a time-varying way for this nonlinear system around the desired trajectory. Okay? But so, because you have this diagram and this kind of simplified approximate calculation, you can see that you're going to have very much the same trade-offs that you would have for linear systems in response to constant disturbance, linear time invariant systems in response to constant disturbances. Okay? So you can see here you have this uncertainty on the dynamics. And we have this. And of course, you can, we have these approximations, so you can see this approximation as being valid at any time. Okay? So all of these quantities change with time. Okay? So, now, of course, the same equation can be written saying that the max of x tilde, or the instantaneous x tilde with some approximation, right, is less than fd over lambda n. Okay. Now, if you see this, that's again something you would have in linear time invariant systems, except here you have it approximately at any instant along this trajectory for this nonlinear system. You see that you have if you want to make x tilde small, right, you see you have two terms happening. Okay? If you want to make x tilde small, one way is to make fd smaller, right? And to make fd smaller means you have less errors on the parameters. So the little toy example where we had a of t between 1 and 2, if you could tell me it's really between 1.4 and 1.6, I would have a better capital FD. Right? So one way to reduce this is to have less error on the parameters. Okay? What is the way to reduce lambda, to increase lambda? Well, is to be able to have faster unmodeled dynamics so that we can have a bigger lambda without interacting with them. All right? So in a sense, this is a ratio between two forms of robustness, okay, or two forms of model uncertainty. Okay? The top one is uncertainty on the parameters, the gains, additive terms. And this, the bottom one, is uncertainty on unmodeled dynamics, okay, which means in a sense uncertainty on the order of the system. Should we have included this extra vibration term? Okay, which would change both lambda and n. Okay, so you have a ratio of uncertainty on so-called parametric uncertainty, right? And fast unmodeled. Now, based on this remark, you can play games which would be exactly the same if you play in the linear case, but again, here you're applying a longer trajectory approximately in this nonlinear context. So for instance, these remarks are detailed in the book, but you could say, well, if I have a complicated model, maybe a way to reduce f would be, capital F, would be to include more terms in this model. Okay, suppose I have a robot dynamics, I can write lots of terms, or I can say, well, perhaps some terms are negligible. But this would imply, computing them, okay, and so the question becomes, what limits lambda? Okay. So let's see what is lambda possibly limited by. And this discussion would be the same in the linear control course. Here, it's more, within the mechanical engineering context, but, it could be in general. So lambda is limited by a number of things which have to do with the fact that you wanted to win a factor 3 or 5 of the unmodeled fast dynamics. All right? So what could there be? Like you could have, for instance, structural unmodeled dynamics. For instance, your motor is going through a shaft, and this assumed the shaft was rigid. Okay, and of course, there's always some flexibility. And so you have a frequency in hertz of the first flexible mode, nu sub r. It's in hertz, so you have a factor 2 pi, and let's say you divide by 3. Okay, so nu sub r would be the frequency of the first unmodeled vibration mode. Okay? And you want, with the right units, to be within a factor of 3 or 5. Again, this is not precise, right? It's just a ballpark. Similarly, you may have a motor time constant, which means that lambda should be less than, again, that time constant of the actuator, and again, perhaps within a factor of 3. You may have sampling effects. In other words, this could be, the real nonlinear controller could be implemented, will be generally implemented on the computer. Okay, so you have a sampling rate. And so typical bound would be you have the sampling rate divided by 5 roughly. This is not Nyquist, by the way. This is much more than Nyquist, much more stringent than Nyquist. If you play with this, right, remember we did this approximation in this boundary layer. We replaced this sine function by a smooth saturation function. For this to work in a sampled system, in other words, you take measurements only at discrete times, it means you don't want to go from here to there in one sample. Otherwise, you don't see the saturation function. Okay? So if you just put the requirement that's at least one intermediate sample, okay, you'll get divided by 4. Okay? If you do this little calculation, okay, still on the corner of your envelope, right? So if you put a requirement that you just have one intermediate point, you'll get divided by 4, okay, which is the minimum you need for this interpolation to be useful at all. Okay? So again, I put 5, but it could be 7 or 8. It's a ballpark. Okay. They could be, so this is the sampling rate. Similarly, you could have measurement dynamics or an observer dynamics, okay? And as you know, if you play, for instance, with root locus and so on, you're quite sensitive to that, so maybe you want a factor 10 from that. So lambda m would be the sensor dynamics, or equivalently or similarly an observer dynamics, state observer dynamics. All right? So you have a few bounds like this. So lambda has to satisfy all these bounds. Okay? And at the same time, of course, because of this, you want lambda to be as big as possible. Okay? So how are you going to pick lambda? It's constant, right? You want it to be as big as possible and smaller than all of these things. Well, just take the minimum, right? So it just says you want lambda to be the minimum of all these bounds. So let's give them a name. Okay, lambda S, lambda A, lambda not S. Let's say sample, and lambda measurement. So you want lambda S, lambda A, lambda sampling, and lambda M. And any other you may have. Okay. Right? Because this has to be as large as possible and still smaller than all. Right? Okay. So that's what you would do. By the way, it's exactly what you would do for a linear system as well. Okay. Except for a linear system, you could be a little more precise about all these bounds because you can play with root locus and stuff like this, or just explicit eigenvalues. So lambda is equal to this because we want the denominator to be as big as possible, right? So you can still play a little more, but still a little space left on your envelope to give intuitive calculations about this, okay? What does this imply? That is the minimum of these few numbers. It means that for the system to make sense overall as an engineered design system, these numbers should be pretty close, right? If you have 1, 2, 3, and 10, something really wrong with this 10, not because it's too big, it's unnecessarily big, right? Right? So in other words, for a good overall design of the system, right, these should be roughly, and here it's really roughly, I mean, it could be within a factor 2, right? But the order of magnitude of all these things should be roughly the same. Because otherwise, it means one is really dominating the others. If, you know, all of these, let's say, are 10 and this one is 1. Okay? Or on the contrary, if one is really big and the other is more or less at the same order of magnitude, it means that you're wasting that one, right? So in other words, you know, if you are on the space shuttle or whatever, you don't expect the astronaut to compute, you know, in real time what should the rocket do, right? You know, because then he or she is really going to be the slowest thing going on in all there, right? Or similarly, if you have, you know, an inverted pendulum in an undergraduate control course, you know, you don't want to have extremely expensive materials, you know, with very, very high frequency of resonance, right? Because anyway, the motor is going to be cheap and the computer is going to be cheap and so on, right? So to have a good overall design, these numbers need to be more or less the same, which implies things about materials. It implies things about choice of motors. It implies things about choice of computers. It implies things about sensors, right? And you can even play a little more with it, as I alluded to earlier. Okay, suppose you have a model, and there's lots of terms in the model, and you say, well, I'm going to simplify my model because the dominant term here, the smallest one, is the sampling rate. Okay, maybe I have 3, 3, 1, 3. Okay, so the dominant one is the sampling rate. So I'm going to simplify my model to make the sampling rate faster. Okay, so you could say, well, perhaps you can buy a bigger computer, right? But suppose you say, well, you know, I'm stuck with that hardware, right? Is that a good thing to do? Well, think of it, right? So suppose like the sampling rate is the active limit. Let's make it, you know, 7717. Okay, so it's the active limit. And it's really staring at you. Okay. Suppose you throw away terms in your model. If you have any reasonable model, the value of the term will vary at best with the time it takes to compute them. Okay, in other words, you'll have started with the important terms and then you'll have added refinements. Okay? So in other words, if sampling is your real limit and and you can't change the computer, by all means simplify the model. Because here this is varying linearly with errors in the model, and this is varying to the power n. Right? So basically sampling should never be your active limit. Right? Because you can always simplify the model so that it goes to the next one. Okay? So you see, out of these very, very simple calculations, you can make all sorts of basic engineering predictions. Right? And then, of course, you can refine them, and you can take teams to refine them and so on. But you can already, like in half an hour, have a pretty good idea of what's going on. Okay, and what are the trade-offs between materials, actuators, sensors, and so on, computation, algorithms. Okay, just based on these very simple ideas. Yes? Oh, similarly, yeah, you're absolutely right. So delay would appear very similarly to this. Okay, so like an extra constant. And again, it may not be a factor of 3, it may be a factor of 5. All these are ballparks, right? But that's pretty much how it would appear.
The delay for different parts would add up.
Yes, of course. If you see this as pure delays, yeah. If you have delays in several things, then you have a total delay, then those would add up, yeah. The reasoning is always the same, right? You place yourself through all of this in a certain time constant range. You assume that things move this fast, and you want to make sure this is a consistency argument. You just want to make sure that this fast is nowhere near things that you've neglected. Okay, that's all. It's just a consistency argument. Okay. Questions about that? So next time we'll go one more step. We'll say, suppose that in all this uncertainty we have between f hat and f, we have a little more structure. Namely, we know that some of the terms of this uncertainties, the a's and b's or whatever, the a's and the d's and whatever happen in this uncertainty, some of these terms happen to be constants. For instance, if you have a robot and it's handling a load, right? It's handling the load well. The parameters of the loads, we'll come back to those, are constants, right? Things like mass and so on. So we will see that in that case, when part of the uncertainty is due to constant, you can go further than just this robust control. You can add what's called adaptation. And adaptation basically will make the system work as if in the system model, in the F, as if the unknown constants were known. So basically, in terms of uncertainty, you'll only have to deal with the time-varying things. Okay? So that will be the next step. Take this and say, well, by the way, I know a little more about my model. Namely, some of this source of uncertainty is due to constants. And we'll show then how to design these adaptive controllers to get rid of the effects of these constants. So that's what we'll do next time.